Hi there, and thanks for tuning into another demonstration of a bot named Sue. In this video, we'll be focusing on the mathematical abilities of the Sue platform. If you haven't seen the first demo video at analycat.com/SueVid, I recommend that you watch that first to get an idea of the functionality in training Sue and getting decisions from it. Also, if you're not specifically a maths practitioner, I really recommend you don't watch this video. It's really aimed squarely at maths and data nerds. The previous video showed Sue with the output as a category, but if you set Sue to output numbers, its behavior changes completely. And I want to deal with some of the endemic problems in mathematics and how Sue solves them. Please don't think that I'm saying that everyone does terrible work or anything like that. What follows are extreme examples of what are normally smaller problems but that are ongoing, and problems that Sue solves. Of course, I realize that there's a lot of great work being done and that we owe a huge debt of gratitude to all the mathematicians that preceded us. But Sue uses a new kind of math that was impossible before supercomputing, and this new approach is considerably more powerful than conventional maths and easier to use. The problem now is our habits. Let's start outside Sue with some data. This is a table of mortality. It tells us at every age what percentage of people die. Sorry if it's a bit morbid, but people spend their lives watching this data, and it makes a great example of a lot of what goes wrong with modern maths. A quick glance at the graph, and you can see that this is an exponential curve. If I ask Excel to add a trend line, I get what looks like an excellent fit. Most of us do this fitment automatically with software. The software, in this case Excel, tells us that the fit is optimal, and we believe it without further thinking. Okay, there's a bit of space here after the age of 83, but I can live with it. The reason I have to live with it is because I'm thinking exactly the same way mathematicians did 400 years ago. I'm forcing this data to be a smooth, continuous curve. In fact, I even see a smooth, continuous curve that's not there. I'm imposing my overtrained approach on the data. The reality is that this data is not smooth and continuous. Nothing is. My old professor in Indonesia, the great Professor Zen, used to say with his German accent, "Adi, Mother Nature has never seen a straight line." But because we've only ever had symbolic, continuous formulas, we need to iron out the kinks and outliers to get a best fit. We've been brainwashed by linear continuity and formulaic maths. What I would like to convey most today is what can be achieved if we stop thinking best fit for one continuous curve and start thinking actual fit. It's quite a task to get past your previous training and see these numbers as they are, but join me in digging deeper and let's see. On this page, it looks like there are only errors above the age of 83, but if I zoom the graph inwards so the Y values peak at 0.06, I see that there are errors above 40 as well. Furthermore, if I zoom deeper, only to the range of 0 to 0.1, the graph reveals a bit of a fitment horror story. For the first part, mortality at age 0 is 0.06, roughly 16 times the mortality at age 1, and going against the trend of the graph. This is called an outlier. Now, it's easy to say that we need to remove this to get a better fit on average across the data, but really what we're doing is removing an important thing to know. Please, again, I know people do better work than this, but it's a good example. If you're looking at averages, removing outliers will improve performance. If we had a better kind of mathematical fitment to track this data, we would have to admit that we're simply removing detail from the information. As you can see though, at every resolution, the fitment is not nearly as good as it looked, and the zero age is a disaster. Luckily, Excel has this nifty feature to show me the formula I'm using for the curve. I click Display Equation on Chart, and I can see here that it's y equals 0.001e to the 0.759x. So I'm going to drop the graph and calculate this in a cell. Now I've added column C, it's the trend line data at each age in the column. And now I add column D, which takes the absolute difference as a percentage of the correct and actual value. Sadly, the problem at age 0 isn't even our worst data point. It's only 98% wrong. At age 10, we blossom to 130% error, even worse, and at the bottom I can see that my average error is a full 30%. Only 9 cells had errors less than 5%. This glorious looking fit that we started with, which our software and training told us is optimal, is in fact a disaster that we seldom look into and question. Because before supercomputing, there simply wasn't a better way to do this. Now I'm going to go to Sue. I'm going to create a new model called Mortality. Instead of the outputs being a category, it'll have a numeric output between 0 and 0.9 with an increment of 10 to the minus 7. The only input variable is age from 0 to 119. Now, of course, when we model in real life, we have many more features than age. But I need to start in one dimension to illustrate what the system does. Later on, we'll look at more nuanced data. I'm going to confirm and save, which takes me to section 2, training the model. This time, instead of answering questions, I'm going to import the data in 2.2. I select a prepared CSV file with 2 columns in it and click import. Of course, I've opened it in the text viewer to make sure that Excel didn't add commas and extra lines, etc. Immediately after importing it, I have a model that I can query, but I'm going to improve it by setting Sue to interpolate between 2 nearest values exponentially. Now, for your convenience, I'm going to put Sue on the right and the original data on the left. At 0 age, I ask and Sue gives me 0.063219, which is almost bang on. At 1 year, 0.0396, and at 10 years, where we had the worst failure of linear mathematics, 0.0093, Sue is perfect. Let's query them all by uploading the data as a query. As you can see from the table, Sue's total area is around 0 as opposed to 30% for the fitted curve, and this is not the exciting bit. Sue's real performance shows when I start asking between 0 and 1. The trend line, as you recall, is a disaster at both points and doesn't do much better in the middle. If I ask Sue at an age of 0.5, it gives me a value of 0.033. This is somewhere in the middle of the value between 0 and 1. What I'm going to do now is query all the ages between 0 and 12 using an increment of 0.1 instead of 1. And then I'm going to export the results to make them clearer. As you can see, I don't have the mortalities in here, so I'll add them, as well as the trend line to give you an idea of the difference Sue makes. So here's the final product. We have the original data, Sue's output, and the trend line output. With the addition of a graph, the full disaster of conventional maths, as well as the elegance of Sue, become crystal clear. All of this area between Sue's output and the trend line represents error and lost information. The original correct data points are marked with blue X's. Now it becomes visible what Sue has done. It has stuck to the original data and added spline interpolators between them. So Sue has not done one fitment. It's done a fitment between each data point between 0 and 12. There are 11 different simple models. These aren't dissimilar to Markov chains. If I zoom in on 3 data points, it becomes easily highlighted. I have one interpolation curve here between 0 and 1, and another one between 1 and 2 over here. They move smoothly, but they're hardly continuous. So instead of literally ignoring all the information that doesn't suit one single curve and ignoring the errors at every stage, Sue uses all the data as is and interpolates to fill in missing values. This is not to be confused with overfitment. Overfitting is when we stick to the data too closely at the expense of future precision. Ignoring the massive mortality at age 0 does not improve your precision going forward. It improves our precision going forward if we only use one curve, but when compared with multiple curves, it reduces predictability. This curve is not overfit. It is the single curve which is unfit for purpose. From here, we need to make a jump into multiple dimensions and features. The real problem here is that the screen is flat and two-dimensional. So I need you to imagine multiple interpolators across all the dimensions of different data. Let's start with this. This is a dataset of buildings in London. They span some 300 years. At the top here, you can see that this is a CSV file, so it's plain text and nothing is embedded into it. I have 5 features here, as you can see. The type of building, the number of floors, rooms, square meters, age, value, and year built. What I'm going to do now is remove some of the years built to simulate missing data. We have our AI engine available as an Excel add-in as well called DPS Data Positioning System. All I have to do is highlight my data. Note that I only have 2,350 data points. I don't need the hundreds of thousands of points that a neural network needs. I go to DPS, click Load Selection, and then I select Year Built as the column I want to model and click Run. Now we have 4 dimensions and a target variable here. What Sue is doing is creating a 4-dimensional space, positioning all the data in it and building a huge number of weighted interpolators between all the points in all the dimensions. I've removed 20 points here, leaving behind roughly 2,300 active points. In 4 dimensions, we have potentially 2,300 to the power of 4 interpolations. Basically, Sue array just under 28 trillion little localized interpolation models at the ready, which it combines as needed to generate the missing points. This approach creates unbelievable deductive power and meaning. So now Sue has estimated the points missing using this multi-dimensional interpolators it created. Let's look at the results. The years, as I mentioned, span 300 years. And given that you have a joisted masonry building with 1 floor, 3 rooms, 337 meters squared, and a value of £1.13 million, good luck deciding on your own that it was built in 2013. But Sue got this one perfect. One of the main reasons for this is that we didn't bring in external data. The set itself has coherence that would be diluted using normal big data. Any AI algorithm requires that dilution because, simply put, it needs too much data. This also won't work with fake data because fake data doesn't have the hidden coherence that this does. Of course, all the predictions aren't perfect. On the overall, Sue has an error of 6%. But if I remove these outliers, I get an average of 3%. That was a joke. Seriously speaking, a few points are driving this average from 3 to 6%. And of course, if I had to audit this list of years built, I now know exactly which ones to focus on, namely those with large margins of error. So imagine if I was modeling life insurance policies. Instead of dumping the whole world into a model, I could choose men like me between 45 and 50 in sedentary jobs with no major underlying conditions and model them as a set. If the AI predicts my rate very differently to my real rate, it'll mean that something is wrong with the pricing. Of course, no modeling is perfect, and this approach will not be ideal everywhere, but in places where it is ideal, it'll outperform anything that was done using conventional mathematical approaches. The last thing I want to deal with again is related to linearity. If I'm modeling satisfaction in a restaurant, it gives me an interesting view on linearity. Let's say I measure hygiene, service, and food quality. Ordinarily, I could decide that each variable was weighted 33% as there are 3 of them, or that hygiene is 20% and the other 2 are 40% of the final score. Whatever I do and however I do it, I'm fixing one weighting across the whole range of the possible values. In the real world, certain variables are very strange. If hygiene is perceived as being below 2, satisfaction will be 0. If it's above 2, it will be irrelevant. Hygiene might be a fatal liability, but never an actual asset. Nobody ever went to a restaurant and had a great meal with great service and one giant cockroach and said the place was great. Look how easily Sue can absorb this complexity. I make a new model, restaurant satisfaction. My outcome will be a score between 0 and 5 with an increment of 0.1. My inputs are hygiene 0 to 5, food quality 0 to 5, and now service quality 0 to 5. Save the model and move to training. In rules, I tell the system if hygiene is less than 3, restaurant satisfaction equals 0. Without taking anything else into consideration. Now when I teach Sue, it'll never ask for anything below 3 on hygiene. The first question is, hygiene is 3, but food and service are a 0. Also a 0. Next question, all 5, so that's easy, it's a 5. Now the food is terrible, but hygiene and service are good, probably a 1. If service is poor, but food and hygiene are okay, probably a 3. At 3, 3, 4, I'm going to give a 3.5. And with amazing hygiene and poor food and service, I'm giving a 1.5. I'm now going to build and tell Sue in 5.2 to use 3 nearest neighbors and exponential interpolation. Let me now ask it some questions. If hygiene and food are a 3 and service is a 4, it gives 3.5. If the food is a 1, it drops to 1.2. If food is a 4, it gives 3.9. Most importantly, if everything is great but the place is dirty, it gives 0. So we've trained a very reasonable model that is completely nonlinear with 6 samples and a rule, and without any programming, without any knowledge of mathematics. Imagine how much work this could save you. Let me end by inviting you to reach out to us, and we'll gladly make you a test account and explain further so that you can test these benefits for yourself. Thank you for your time.